Hey everyone, and welcome. Today we are diving deep into the amazing world of organic chemistry. I'm talking about the science that explains the molecules of life, the fuels that power our world, and honestly, so much more. You ready? Let's get into it. So, let me kick things off with a question for you. What do your DNA, the fuel in a car, and the medicine that keeps you healthy, what could they possibly have in common? I mean, they seem totally different, but they all share one fundamental secret. Any guesses? Well, the answer, believe it or not, is carbon. This single element is the backbone for millions upon millions of different compounds. It's the ultimate building block of the molecular world, and this is the incredible realm of organic chemistry. So, what is it about carbon? What makes it so special? To figure that out, we have to look at its most basic properties, the unique features that let it create this just unbelievable diversity of molecules that we see literally everywhere. You know, it all really comes down to two remarkable abilities. First up is something called catenation, which is just a fancy way of saying carbon atoms can link up with other carbon atoms, forming these incredibly long and stable chains and rings. And second, tetravalence. Every single carbon atom can form count 'em, four strong covalent bonds. I mean, think about that for a second. That combination is the perfect recipe for building staggering complexity from simple parts. And get this, the way carbon uses those four bonds is what actually determines a molecule's 3D shape. It's all because of a concept called hybridization. So when carbon forms four single bonds, it creates this 3D pyramid-like shape called a tetrahedron, like you see in methane. But when it forms a double bond, the molecule flattens out into what's called a trigonal planar shape. And with a triple bond, it snaps into a perfectly straight line. This predictable geometry is absolutely crucial because a molecule's shape is what dictates how it will behave, how it connects, and how it reacts with everything else. Shape is everything. Okay, so we know these molecules have all these cool, specific 3D shapes, but how in the world do chemists actually manage to represent these complex structures on a simple 2D surface, like a screen or just a piece of paper? Let's take a look. Well, there are a few ways to pull it off. You've got the condensed formula, which shows every single atom. It's thorough, for sure, but man, it can get really cluttered with bigger molecules. That's why chemists came up with something way better, the bond line formula. And it's just such a clean and elegant shorthand. Every corner and every endpoint of a line represents a carbon atom, and you just assume the hydrogens are there. It's simple, it's efficient, and it lets you see the core structure in a single glance. But to really solve that 3D problem on a 2D surface, we use what's called the wedge and dash formula. It's a brilliant little trick. A solid wedge means a bond is popping out of the screen, coming right at you. A dashed wedge shows a bond that's going back, away from you. This simple convention lets us accurately visualize and truly think about molecules in 3 dimensions, all on a flat surface. Now, with literally millions of different organic compounds out there, you can just imagine how chaotic things would get without a crystal clear naming system. And that's where the IUPAC, the International Union of Pure and Applied Chemistry, comes in. They created a universal language for naming molecules so that a chemist in Tokyo and a chemist in Toronto are always talking about the exact same thing, no confusion. And this whole system is built on a really beautiful logical foundation. The core of a compound's name is based on the number of carbons in its longest continuous chain. So 1 carbon gets the prefix meth, 2 is F, 3 is prop, and so on. Seriously, if you just learn these first few prefixes, you can start to decode the names of all sorts of simple hydrocarbons. It's kind of like learning the alphabet of chemistry. A name isn't just some random label, it's basically a step-by-step set of instructions. Let's take a look at this one, 6-ethyl 2-methyl-nonane. We can just deconstruct it piece by piece. Nonane tells us the main chain has 9 carbons. The 2-methyl part means there's a 1-carbon branch sticking off the 2nd carbon in that chain. And 6-ethyl tells us a 2-carbon branch is on the 6th carbon. See? It's a perfect blueprint for drawing the molecule from scratch. All right, but now, this is where things get really interesting. What if you have 2 molecules with the exact same list of atomic ingredients, the same exact formula, but they're arranged differently? This brings us to the fascinating idea of isomerism. I mean, think about it like this. You've got the exact same set of Lego bricks, but you use them to build 2 totally different things. How does chemistry pull this off? Well, the secret is all in how the atoms are connected to one another. So there are three main types of these so-called structural isomers. Chain isomers have different branching patterns in their carbon backbone. One might be straight, another might be branched. Position isomers have the same carbon skeleton, but an important group is just attached at a different spot. And then you have functional isomers, which are the most dramatic. They contain the exact same atoms, but are arranged into completely different types of compounds, which gives them wildly different chemical properties. This is a huge deal. It's why molecular diversity is practically infinite.
Okay, so we've talked about what molecules look like, how we draw them, how we name them. But chemistry isn't static, right? It's all about action, about change and transformation. So how do these molecules actually react with each other? To understand that, we need to peek into the world of reaction mechanisms.
You know, every single chemical reaction has to start somewhere, and that's by breaking a bond. This can happen in two main ways. In what's called heterolytic cleavage, the bond breaks unevenly. One atom gets greedy and takes both electrons, which creates charged ions. But in homolytic cleavage, the bond splits right down the middle, nice and fair, with each atom getting one electron. This creates highly reactive neutral things called free radicals.
And in those reactions that form ions, you've got two main characters on the stage. First, you have the nucleophile, which literally means nucleus-loving. It's rich in electrons and it's on the hunt for a positive center to donate its electron pair to. Its counterpart is the electrophile, or electron-loving. This one is electron-poor, and it's searching for an electron-rich spot to accept a pair of electrons. It's this fundamental attraction, this little dance between the electron-rich and the electron-poor, that drives the vast majority of organic reactions.
All right, we've been deep in the theory. But what does this look like in the real world, like in an actual lab? Well, whether a compound is made from scratch or carefully extracted from something natural, like a plant, the very first step is always purification. You've got to isolate what you want from all the other gunk. And chemists have this whole amazing toolkit to get the job done. Sublimation is a neat trick for solids that can turn directly into a gas, skipping the liquid phase. Crystallization is a classic and really powerful method for purifying solids. For liquids, you've got distillation, which is perfect for separating them based on their different boiling points. And then there's chromatography, an incredibly versatile technique that can separate even the most complex mixtures with just amazing precision. But once a compound is totally pure, the job's still not over. Nope. The final, and I mean critical step, is analysis. Qualitative analysis tells you which elements are present, while quantitative analysis tells you the exact percentage of each element. This is really the moment of truth, where chemists confirm that they've successfully made or isolated the exact molecule they were after. You know, this whole journey from the earliest observations all the way to our powerful modern understanding is just so well captured by this one quote. It was really when we finally started to understand electrons and how they form covalent bonds that organic chemistry truly transformed into the predictive and creative science that it is today. And that, everyone, is our whirlwind tour of the fundamentals of organic chemistry. We've seen how the simple, elegant rules that govern one single element, carbon, can give rise to the mind-boggling complexity of life itself. It really makes you stop and wonder, with this amazing power to design and build molecules from the ground up, what will we create next? Thanks for joining me on this one.